So today we are going to cover arrays, and so there were two levels that, well, one of them got misnumbered. The matrix one got misnumbered, and so did the 2D arrays one was properly numbered. So section 3.8 2D arrays and 3.7 matrix. After today, you can solve those two levels.
Hope so.
All right. And then the only level that you can't solve would be the struct level. Okay, so.
I have been.
Yeah, so don't try. Yeah, sorry. I think I sent a message earlier in the week. Like the numbering's all messed up. So like the 3.10 levels you could do in 3.7. I mean, yeah, I got to fix that. So I'm gonna. Yeah, I know that's an issue. Very confusing. The other thing that was confusing was somebody emailed me about the fact that the D2L assignment deadlines had completely different than the website. So the website was correct. I updated the D2L. The assignment 4, which I haven't even assigned yet, which you can't even do, that's due March 7th. That's not due next week.
3, right?
Assignment 3. Sorry.
Yeah, okay.
Assignment 3
Yeah.
is March 7th, and then assignment 4 is March 14th, I believe.
So that's what
And you guys, that shouldn't be on your radar at all.
Okay.
You guys should just be doing binaries, and then, just focus on the binaries.
Can you let us know before it's like time for the 7, because like it really takes STFs are complicated.
Yeah, but you'll know. Well, so hopefully all of your binaries will be done before I cover
All of the CTS for the term.
for chapter 3.
Oh, okay.
There's like one more set, but these are sort of fun. These are fun
Okay.
levels for chapter 8, I think, or something like that.
Because that's not fun anymore.
Yeah. So then you'll know when I cover the lecture on single instruction multiple data. That is the time that you will finally be able to do assignment 4, and I'll let you know. And then by then, your other chapter 3 binary should have been all completed, so that you can focus on that.
Because technically arrays is related to the 7.3, right? Because we have a matrix in 7.3, like we have 2 arrays and we multiply them, so chapter 3 is.
That is true. Yeah, you'll need a little. Yeah, you might need a little bit of array knowledge in that. You'll need a lot of different things. You'll need embedded assembly. You'll need to know the SIMD instructions. You might need to know about loop unrolling, which is a chapter 5 thing. So yeah, there'll be a lot of things that come together on that assignment, but it's a very short assignment. Okay, so I am going to cover how arrays are not only allocated in memory, how they're accessed by your program. So just to brush up your memory, you don't have it, okay. These are how you declare arrays. So you define a type. You have the name of the variable, and then the size of it, how many elements there are. So this is an array of 80 characters. This is an array of 40 integers. In terms of allocating arrays in memory, the basic principle is that you allocate it contiguously, no blank spaces. So if you have an array A, it has a type T and a length L, that means L is the number of elements, then this is contiguously allocated in a region that is L, which is the number of elements, times the size of the data type, size of T. So for a string array of 12 elements, this is 12 contiguous bytes from x to x plus 12. For an integer array of 5 integers, this is 5 integers, each 4 bytes long. So a 20-byte integer array. And then here are 3 arrays that have the equivalent allocations, an array of 4 longs, an array of 4 pointers to characters, and then an array of 4 doubles. So these are all 8-byte quantities, and the size of this is the length, the size of long, which is 8, times the number of elements. All right? And then you can see these are the addresses of successive elements. So the address here is x, and then x plus 8, x plus 16. Okay, so that's an array allocation. One of the other things I want you to recall is that the pointers and arrays are closely related. The name of the array can be referenced as if it were a pointer.
Because it is.
Was it?
Because it is.
Because it is.
In C.
In C. So here we go. Here's long. a long array called A has 5 elements. I can have this pointer, long pointer, LPTR. It's a pointer to a long, and then I can do this assignment. LPTR is equal to A, and this is basically the address of the first element of this array. And I can use this literal as a long pointer. The other thing to recall is that there are 2 ways of accessing array elements. The typical way that all of you are used to is to use the square brackets. So this says get the third long integer in array A and then assign it to I. You could also use pointer arithmetic followed by dereferencing. So if you recall pointer arithmetic, it's done based on the type of the pointer. So you could do something like this. Say A plus 3, and because A is, the type of A is it's a long array, A plus 3 is actually going to go to the third element in that array, which is 24 bytes, because A is 8 bytes, the long is 8 bytes. And then dereference that. This is equivalent to that. Yes?
Whole thing is because addition in C is necessarily commutative. That means that you can write 3 plus A and dereference that. And because under the hood, the brackets are represented as the pointers, you can actually write 3 and then in the brackets A, and that still works.
3 and then brackets A, I don't know if that works.
So like I've adjusted that. It'll actually work because under the hood, the top one is the C, it's out, then it's the bottom one to the compiler.
I remember actually.
So they're cumulative. So
that in 162.
Wait, you mean the 3 as a literal bracket A?
yeah, that works.
Okay.
Carl Pang said that a lot during the lectures. Yeah.
Oh, all right.
Because
I've never seen it.
because addition is commutative.
It's adding the number 3 to your pointer.
All right. Interesting.
So, the only thing the brackets are is syntactic sugar for the pointer dereference.
So one of the things is I'm old school in C. I do C89. This might be new school C that she's teaching you.
It's C++.
Yeah, that was C++.
Oh, that's C++.
So it's
Oh, there you go. That's C++. Well, I don't know anything. I admittedly know I used to develop in C++, but I really...
I actually had the impression that C and C++ are very much the same, but the more I read the book, I realize that there are certain things about C that they're actually very different. Even small things like
Completely
that.
different language, yes.
They're actually different. I always thought they were, it's just similar but better than C++.
It borrows syntax. It tries to borrow syntax
But they're different.
and then add a bunch of other things to it, yeah.
So for example, in like C++, doing pointer arithmetic is faster than using the indexes. So in some of Carlos' classes, it's like, if you really need the speed, do pointer dereferencing.
Whoa.
Exactly
Yeah, you're gonna steal my thunder here. I got that. So yeah, let me not have you take my lecture. But no, we'll get to that because the compiler actually will see your code and will change it to a different implementation, a good compiler. So you can help it obviously by giving it a code pattern that obviously will compile to a more efficient way. But yeah, the compiler is actually smart enough to do that for you. So for this particular case, you can do this, which is more obvious to people reading your code, and still get the good implementation. So that's what in fact I would rather you do this than do this to the compiler and the person the people reading your code after it, like the TA. TA is going to be like, what? What is that? Yeah.
The only reason that doesn't really work in C++ is because a lot of the times, since you create arrays of objects and do that, it can't really go all the way through and find all the types and know how many whatever. But if you manually create the pointer arithmetic for everything, it's like, oh well, that must be right.
Yes.
Double check it.
So we'll see. Circle back around the last slide of this lecture, and we'll talk exactly about this. All right. So here is some review. If A is at hex 100, what is the value of A plus 3? You can do the math. In hex. In hex. Hex 100, A plus 3.
103.
What is it in hex? Not 103, though. It's not in hex.
103.
A is a long, an array of longs. So If A is at hex 100, what is A plus 3? Yes. Hex 118. Is that confusing? So you recall when you do this arithmetic on A, it's done based on the size of the data type. Size of the data type is 8 bytes. This is A plus 24 decimal. And then you have to convert that to hex, because I wanted it in hex. So 118. Or you could just say this is at 100, this is 108, this is hex 110, hex 118.
Well, if it's 8, then every time you do it twice, you're incrementing a second.
By 16, yeah.
So it just increments that by 1.
Yes. Okay, so this is a refresher on how arrays are allocated. So here are some examples of arrays, and I want you to be able to understand these this table. So arrays A, B, C, and D. You have an array of characters, an array of pointers, an array of longs, and an array of floats. So for the first array, the element size is 1 byte, because it's a character. Total size is 12 times 1. The start address is x of A, and then the element I, so if you do A of I, the address is x of A, which is the base, plus I. For B, the element size, because these are pointers, each pointer is 8 bytes. So the total size of this array is the number of elements, 8, times the size of that element, and this is a pointer, so the size is 8 as well. Total size is 64. When you do B of I, you're going to the address x of B plus 8i. Does that all make sense? And so on. The long is element size 8, and the float is element size 4. Okay, so
what size? The pointer's always 8.
in x86-64, the pointer is always 8. Yes. Yes. All right. So, yeah, 64 bits, 8 bits in a byte, 8 bytes. So here's an example of some accesses to an integer array val. And in this integer array, I have the integer 1, 5, 2, 1, and 3. And this integer 1 is stored in 4 bytes. This integer is stored in the next 4 bytes, etc. So given a reference here, give me the type of data that this represents, and then the value. So for the first one, what is its type? It's an int. What is its value?
Val 4?
Yeah, what is val for?
1.
It is 0, 1, 2, 3, 4, because you start with 0. So yeah, that's correct. If you see val by itself, what is its type? A pointer to what? An integer. Yeah, you have to always associate a type with that pointer. The value is it's not 1, it's x. Yeah, because 1, this would be val of 0 would resolve into 1. When you use val by itself, you just return the address, and these are the addresses on the bottom. Okay, so val plus 3, what type is that? Pointer to an integer. What's its value? X plus 12. This one, the address of val of 2. X plus 8, yep. Integer pointer, x plus 8. Val of 5, out of bounds is correct. What's the type? Well, it's considered an integer because you wrote it. The assembly code is going to assume whatever's there is an integer. The star of parentheses val plus 1, integer, it'd be 5. So val plus 1 gets you to this, dereference it, and you pull out the 5. Oh, here, let me get you the last one. Let me take a picture of that. No, not necessarily. If this has been allocated, it'll just give you whatever garbage was there. It probably wouldn't segfault because unless this is the last byte of your page. So typically pages are 4 kilobytes. So maybe 1 in 4,096 chance of it segfaulting. But yeah, most likely it's just garbage. You get whatever was there. All right. So first practice problem. My scrap paper here. I have true scrap paper this time. I actually was digging through the recycling. I felt bad about like bringing copier paper in here. I was like, that's not really scrap paper.
Whether it's segfaults or not depends on the memory boundary.
Okay, so array S, the element size is 2, because it's a short. The total size is 2 times 7, which is 14. And then the element I is located at the base, x of S, and then plus 2i. Good? These are shorts. 2 bytes. Shorts are 2 bytes. Ints are 4 bytes. Longs are 8 bytes.
Poster with all this and just put it up.
Yeah, yeah. All right. Element size for T is 8. It's pointer. The total size is 3 times 8, which is 24. And element is at plus 8i. The last one, the integer, the element size is 4. Total size is 32, so it's 4 times 8. And that element is at u plus 4i. Okay. So, arrays as function arguments. So the basic data types, when you pass them as function arguments, they're all passed by value. You basically copy a version of the int, of the char, of the float, onto the stack or into registers, and then the function that you call gets a copy, passed by value. So what about arrays? Do you think they're passed by value? Like you put the name of the array as a function argument, are you doing passed by value or passed by reference? Passed by reference. Oh, good. You guys are on top of things. Because then, yeah. All right. So if you do something like this, you have an array of 32 million longs, and you decide to call foo with that array, you should know whether or not that copies 32 million longs onto the stack, or if it passes a reference to it. Because one is going to blow the heck out of your machine, and the other one's just like, oh, it's, yeah, just a reference. So when you do something like this, well, the first thing is, what is the function declaration of foo? What is its return value? What must be foo's return value? A long, because it's being assigned to a long. And then what is its function argument? Would be the type of the argument that this function takes in?
Or long array.
A long star. Yeah. So because when you use exp as itself, it's an address. It's the address of the first element. So it's basically a pointer to a long. Right? So the name of the array is equivalent to a pointer. So you are passing this array by reference. Because now the pointer that you pass it is an address, and then the indices are being done off of the caller's variable. This is tricky, right? This is not, so knowing what stuff gets called by value, or passed by value, and what stuff gets passed by reference, this actually matters, and you have to know these. These are more like rules. These are conventions that the C programming language is putting in here. And with any programming language, you need to know the rules of the language so that you know that this is not going to copy 32 million longs onto the stack.
Do we have to declare the pointer, or can we use the brackets like C++?
You can use the brackets. You could say long bracket of f if you'd like, yes.
That makes it a constant.
It does make it a constant, but you could, yeah. Let's not go there because that's not, yeah.
If you don't want to modify it.
Yeah, forget the rules. You know what? I'm not going to give you something incorrect, especially because it's being recorded. So yeah, that's not a level I'm going to go to today.
Oh,
Whether or not if you do a f bracket bracket, I think that means it's static and you can't. You can definitely not reassign it.
You can't reassign the pointer, but you can change the values.
You can
at that
you can change the values in it, but it's a little different than just doing this because here you can then reassign f to point to other things. Whereas if you use the bracket bracket, that's sort of like a constant literal. So yeah, and that's not a level of C that I'm asking you to know right now.
So it's the difference between making the pointer static.
Exactly. That's the exact terminology. Yeah.
There's some cool stuff in C++ that you can do to make it so you can test your code really easily, like passing in char array rather than a char star.
Okay.
Anyways.
I'll just have to go without that that coolness in my life. I'm not going back to C++. I'm sorry. What's that?
Not gonna be
Yeah, I do have more of trauma. Some people, they can wrap their head around all of that, and more power to them.
talking about what?
All the different types of syntactical things and what they give the language.
All you need is more abstraction.
And
Consistent abstraction is fun.
yeah, there comes a case where the language has a lot of things that are overcomplicating the language itself. And if you guys know Python, Python is trying to do the opposite. But even in its first couple of iterations, it did have things that what is this guy's name? Guido? I forget his name. The guy who did, but he was like, I wish that wasn't in there, and he got rid of them eventually. So typically languages have too much stuff, and people aren't getting rid of the cruft, and that makes the language sort of like PHP really difficult later on. No comment about C++, but I just, yeah. So practice problem. Now this will be a walkthrough actually. Consider the following code. You have a character pointer array, an array of character pointers, p lines, and then within this array, first we'll talk about 3 character pointers, AP, BP, and CP, that point to strings, ABC, BCD, and CDE. And then for each element of this p lines array, I'll set it individually to these 3 pointers. Okay, so this is like argv. If you guys remember argv way back when. Argv is an array of pointers, and each pointer is pointing to one of your arguments in the command line. So what are the types and values for p lines as a literal? What would be its type?
Line is a pointer to a pointer.
Pointer to a pointer. Char star star p lines. All right. Now, one of the power of 10 rules is to avoid too many levels of indirection. This is just right. Like, I think anything beyond 2 levels of indirection like that, a pointer to a pointer to a pointer, I think that starts to blow people's brains up. This already is a stretch.
Yeah.
But that's what that is.
3D arrays are fun. Come on.
Yeah, that's all right. So then, what is p lines of 0? What is its type?
Star.
This is just evaluating it as itself. What does it return?
Char star.
It returns a char star, and what is its value?
Whatever the index is of the first language. If you have a good compiler, it's 0.
It's AP.
Oh, I'm sorry.
Right, because we assigned we assigned p lines of 0 up here to AP. The type of AP is a character pointer to that string. So yeah, character pointer AP. Star p lines. What would that be?
Same thing.
It's tricky. Same thing, right? You're dereferencing this p lines, and p lines was a pointer to a character pointer. And so what happens when you dereference it is just going to return the very first element, which is p lines of 0, which is AP. All right. Star p lines of 0. What is that going to return? The character A. Yeah. So when you go here, so p lines of 0 gets you the AP. Star p lines of 0 will go into here and we'll take the character A and return that. Star p lines. Same thing. You dereference this to get this. You dereference that, and it'll return the first character. P lines of 0, 0. Same thing. P lines of 0 will give you this, and then when you index AP of 0 will give you A, character A. Yeah.
Which means two-dimensional arrays are the same thing as pointers to pointers.
Yeah, pretty
So
much.
you do pointer arithmetic to go all in the middle, just from huge, messy, nasty pointer arithmetic. And then since all pointer arithmetic is commutative, you can make it completely unrecognizable to any.
Yeah, so there used to be this, in fact, there still is this contest, this obfuscated C contest. I don't know if you guys have seen it, where you do this kind of nonsense to confuse people as to what your program actually does. Yeah.
Like multi-dimensional arrays, if you didn't want to allocate all the data space for it, wouldn't you need to use multiple levels of indirection to be able to point to all of the different levels of.
Oh, if you if you have a sparsely populated large dimension array,
Right.
and you did not want to actually store that, yes,
You didn't want to store all the data.
You would have to do
no
something
pointers,
else.
not much.
Yeah, yeah. Sort of like if you guys have seen an associative array or a hash table array, you would implement that not contiguously, obviously. You would just do some sort of indexing table lookup thing. Yeah.
Is there any difference in the speed between all this? I mean, like,
No.
the last ones are the same.
Uh,
So the way they're implemented, is there any significant difference?
No with an asterisk. So for this one, no. This is too trivial. But if you had like P lines of 1,000 and then 2,000, then maybe,
That would be slow.
maybe you're doing, And then you have to calculate indexing code. Depends. And we'll see where it depends later on. Okay, so let's talk about arrays and accessing arrays in assembly, because now we know how they're allocated. How do you access them? And typically, because they have very regular access patterns, you're typically accessing things sequentially. Optimizing compilers are really good at giving you fast indexing code. All right, but the thing is that the output may not look at all like the input. It might transform your array access into, for example, a pointer-based implementation. Okay, so in order for me to start with this, I am going to walk through how array accesses are implemented in assembly. And so in this case, we have an array, capital E, 20 integers, and we're going to write assembly to move each one of these expressions into RAX. So that is our task. And to begin with, the register RDX has the beginning address of E, and RCX has the index that we want to get for things like this expression and these two expressions. Okay, so that's what we're going to do. The first expression that we want to evaluate is to get E as the literal into RAX. And so E is an integer pointer. It points to the beginning of this array. The value is going to be x of E, but in assembly, what would be the assembly code that would do this? A move of, what's the source?
RDX.
What's the destination?
RAX.
RAX. So that's the command you would want to do to implement this, to move this expression into RAX.
I'm confused about the entire. What are we doing?
We are writing the assembly to move each one of these expressions into the result, and the result we're saying is in RAX.
Sorry.
Yeah. So E of 0 is an integer. It's a very first integer in this array. And you're going to go into the memory location of x of E, and you're going to pull that data from that location and move it into RAX. So the assembly code is going to be, so all these are moves. But what kind of move?
The reference. No, it's going to be whatever that data.
You think it's a move quad? How many of you think it's a move quad?
No, it's not.
What kind of data is it? It's a int. An int is 4. Move L. Yeah, move long. Yeah, that's sort of trivia. But yeah, remember it's byte, word, long word, quad word. All right. So this is move L. Parentheses RDX, right? Because you're trying to get to the memory location, so you're going to use indirect addressing. The address that you want to get is in RDX because it's E of 0. And then you're going to move it to EAX because this is a 4-byte integer. You're not going to move it to RAX because RAX is the quad version of your register.
So does that command you moving into EAX the lower half of the register?
Mhm.
Does it do anything with the top half bytes?
It's not supposed to, but I think the semantic in the architecture is that it zeroes it out.
Okay.
Yeah.
Oh, so you can't do that to make it so you have more memory. Like, I mean, like values you have in RAX or RAX and EAX.
Yeah, I do believe this is implemented as a moves 0 extend long, so it ends up whacking the top 4 bytes.
Then you can start two things in one register. Like separating like EAX and
I don't think so. Yeah.
like if you had 232 bits in 164.
I don't think so. But you could test this actually. You could actually write a program to
I
test it.
actually captured it so many
You
times.
could have moved along and shifted up into the high order and then moved another along in.
I don't think so. I don't think so. I'm not sure. Yeah. I'm not committing to anything. All right. So here's a tricky one. Here's this array index E of I, and you know the index is in I. This is one where you're gonna have to think about it. Move L, okay.
It's going to be RDX, comma, size, but the size is going to be so it's going to be 4 times whatever is in RCX. So it's going to be arrays RDX, comma, RCX, and then it's going to be
Comma
4.
Yeah.
Can we use the last effective address for that?
For which one? For
the
this one
last-
up here?
Yeah, because I mean the Leah.
This one up here, you can do an LEA, yes. You could do an LEA quad parentheses RDX into RAX, and it'd be the same.
But for the last one, because we can use the Leah.
Oh, wait, this one?
Yeah.
Oh no, because you're actually trying to get the data at that array location.
Because
Yeah. If you did this is an LEA for sure,
okay.
right? You're getting the
Yeah.
address. This is actually getting the integer stored at E of I. So that's why this is a move L. So you're taking the index, multiplying it by the scale. So this is why you're using 4, because the type, the size is 4. 4 times the index, that gets you to this location, well, assuming you add the base to it. So this is the start of the array. 4 times the index gets you to E of I. Then you dereference with the parentheses, and then move that integer into EAX.
Okay, so whenever we see that, it means that we're moving into array for positions.
This is the scale factor.
Yeah.
Yeah. RCX positions.
Okay.
RCX, yeah, is the index.
Is it pretty common to see RCX be the indexer variable? Because I've seen that a lot in some of the assembly.
Yeah.
It is?
Yeah.
Yes.
Just
The answer is yes, then.
Yeah.
He
No,
said-
RCX is
You're right. Actually, RCX is now used as a counter for a lot of things. And we'll see that there's a repeat instruction now in x86 that uses RCX as a counter.
I mean, every time you see RCX, which is like add it, if you see add quad and then you see RCX and 1 in front of it, you know that you're counting for something.
All right.
And that's at least how I figured out things.
Okay. Yeah, it depends on the compiler, right? The compiler would be like, oh yeah, RCX is the flavor
Also,
of
those
my day.
things can be different at different compiler.
It could be, yeah.
Okay.
Yeah. But typically, so stuff like, the return address being an RAX, that's pretty common everywhere. So maybe it would allocate that all the time, but yeah, I don't know. Okay, the next one. The address of E of 2. It's an integer pointer, and it's the value is the base plus 8. So what is the instruction? What kind of instruction am I doing?
Yeah.
Load effective address.
and it's the same thing. This is actually or RCX.
There's no RCX in this one. Because there's no I in this expression.
Oh, I'm sorry.
Right?
Yeah,
It says, hey, this is a constant, and I know the size. I can just, compiler would be like, I can do math. Compiler would be like, oh, I'm just going to put an 8 there. 8 times the base plus 8, right?
Plus 8. Yeah.
Yeah. This is 2 integers, so it's like, yeah, I can do that math. 2 times 4 is 8, so LEA quad 8 RDX is the address, and I'm doing an LEA quad, so I'm keeping this as an address, moving it into RAX.
Okay, so this is an address.
Yeah.
But
It's calculating this, the address of this, and rather than going and dereferencing that,
Okay.
it's an LEA quad, it's just going to return that address.
Yeah, it's kind of weird that they keep the parentheses even
Yeah. It's
Yep.
though
kind of
you're. Yeah, right.
confusing.
Yeah.
Because this is technically a memory mode. Like, you want to specify any memory location using the typical memory mode. You just don't want to dereference it. That's why the parentheses are there. That's the notation that we have defined to access memory. And since you're trying to get a memory address and not the memory location, you can still use the same syntax, but the semantic of the instruction is just don't do the dereference. Just give me the address. But you take advantage of all of the scaled index, all of this other stuff that's in your addressing logic, you take advantage of that.
And the return will be an address. The racks will have like an hexadecimal.
This is an address, yeah. That's a pointer that's in RAX now. Yeah. All right, E plus I minus 1. This will give you an integer pointer, and it's 4 times I minus 1. So this is 4I minus 4. So given this, what is that command over there?
Load effective address minus 4.
Minus 4, uh-huh.
I don't know the rest, RDX.
RDX, RCX, comma 4. All right, you guys got it.
Let's capture the flag.
I don't. Do I have a CTF that does that? I don't have a CTF that does that, but
in some cases it does it.
it does that.
Yeah.
Okay. All right.
I guess the compiler does it.
I'm tired of these. But yeah, you can go through the rest of them.
It's like, hey, that's good.
All right. You can do some more though.
Thanks.
So here's practice problem 336. Short integer array. The index is in RDX and the address and the index are in RDX and RCX respectively. So just like the previous example. For each of the following expressions, give its type, a formula for its value, and an assembly code implementation, and store the result in RAX. RAX, if it's a pointer, make sure you store it in AX, which is the low 16 bits of the register, if it's actually a short, right? Because this is a short. So and then the move when it's a short is a move W, right? So shorts are 2 bytes. So the move W is the thing you want, and then you're going to move it into AX because that's the low 16 bits of that register.
It's a bit redundant when you're specifying, move quad, move long, move byte. Maybe I'll just specify the width of the register you move in
Yep.
as well. Can you say move byte and okay, well, of course, you move in the lower.
Maybe if you want to see if the assembler is smart enough to say, I'm going to trust the extension of the instruction and completely ignore what you've written in the registers, the assembler might be able to do that. I don't know. I haven't tested it. Or it might give you an invalid opcode and say, yeah. Well, typically you're never hand coding the assembly anyway, so then it would be the compiler knows. Yeah, for sure. Okay, so S plus 1, the type is a short star. The value is the base plus 2, right? Because these are short integers. So LEA quad 2 plus RDX, which is your base, into RAX. S of 3 is a short. The value is the memory location, or the memory at the address of the base plus 6, because it's 3 times 2. Move word 6 RDX into AX. Good? Makes sense? Yeah. The address of S of I, here you're going to actually use the index register RCX. This is going to be a short pointer. The value is the base address plus 2 times I. And the instruction is an LEA quad, parentheses, RDX is the base, the index is an RCX. Your scale factor is 2 because it's short, and that goes into RAX.
When you say address X, you're talking about the address that the array starts at?
Yes.
So not the pointer to S, which is the pointer to...
It's the same thing.
Well, if S is a pointer to the start of the array, then do you have a pointer that points to S?
No, S as a literal is basically representing the address. Now, if you said foo is equal to S, then yeah, you have foo as a variable in memory that points to S. Is that what you're talking about?
Yeah.
Maybe. Yeah, okay. So then, yeah, but S as itself is just the same as the address of S of 0. All right, the next one is 4 times I plus 1. This is a short, and you go to the memory address of 2 times this. So this is the memory of the address of S plus 2 times that, which is 8 times I plus 2. And so this is a move W. Here's your 2. And then RDX is the base. And then the scale is 8 times I. And then that moves into AX. You would never see this. But this is just for a practice problem.
What if you want to get every odd one after the 4th iteration of where you're at?
Yeah, if you can come up with a program that needs to do that,
I'll go down that way.
that needs every 4th one after the first, yeah, maybe. Yeah, maybe. Who knows? Maybe that's your encryption scheme.
Or you just have to assume like each of the rotation cycles. It's like they're mathematical structures.
I'm sure you could come up with some. Maybe you're sampling, right? You're like the Nielsen folks. You're sampling every 4th
Maybe,
short person. I don't know.
maybe you stored your data as another data type, and now you're pointing to the same area and calling it short so that you can access.
Oh, yeah. Maybe you have an array of, let's see, 2 times 4.
Yeah,
So you have an array of longs, and then, but you're you're using that to store shorts. Yeah, that would be. You're doing data hiding, yeah, because then you would have to get the first byte offset. All right. The last one is similar. All right, let's go. Let's go to the next thing. All right, multi-dimensional arrays. Okay, so in C allows for this. You just use multiple square brackets after the variable name. So this is in a 2-dimensional matrix X of integers. So an R by C, and this, the number of rows and the number of columns, R by C. And so the dimensions of the array, if you have this declaration, these two things must be predefined constants. You are not allowed to declare an array that has a variable number of rows and columns, a runtime sort of determined number of rows and columns. When you declare this in C, the C compiler must always be able to generate proper indexing code. And if these are very unknown, then it's impossible for the compiler to generate it. So that's why these things have to be constant. You can have higher dimensions by just continuing to add the square brackets.
If you want to make it. I was just going to ask, do you have to use malloc? Like, I saw a couple of different versions of like creating.
Okay, jumping ahead. If you wanted dynamically dimensioned arrays, you'd have to use malloc. And then you would have to write your own indexing code in your program.
Yeah.
Yes. That's the last slide, second to last slide, I think, of our, yes. But if you want it to be allocated statically at compile time, these must be constants. Okay, yeah.
So does that mean that multidimensional arrays in C, when they're statically defined, are actually contiguous inside of that entire set?
Yes.
Okay, I had a question I think that I might have posted about that, and I was like freaking out. So I was like, why in the world is never like?
It is contiguous. All of this is contiguously stored. And then, because it's contiguously stored, the compiler knows exactly where stuff is.
What does mean contiguous?
It's
The word contiguous, like,
one after
what's the meaning of it? Like, contiguous.
contiguous, uninterrupted, all in a row.
Okay.
All the data for this matrix is stored right next to each other. There are no
Okay.
gaps. Yeah, contiguous. So, okay. Moreover, they're contiguous and they're stored in what's known as row major order. So that means all of the data in a specific row are stored next to each other. Okay, that's how you organize the data in a two-dimensional array.
So, like, if the row was like, let's say it was 5 by 5, so it would be 1, 5, 15, like, for each row. Like, I don't know, 5.
Aha, but we have these two-dimension labels. So if you wanted to take a two-dimensional array and access it using one dimension, that's what you were talking about. But we're talking about using the two-dimensional array access, the notation. So this means A of 0 and then star, this is all stored in memory first, and then that's followed by A of 1 star, where the column goes from 0 to the number of columns minus 1. So A of 0, the row 0 is first, then the row 1 follows it, then the row 2, etc. That's how we're storing this array. It's important to note that the last dimension, the far most right one, is the one that varies the fastest with linear access through memory. As you are sequentially going through memory, your rightmost index is the thing that's being incremented all the time. Yes?
So does that mean that you could take an array and let's say it was really big and you want to make it a little bit easier to parse out or something, you could treat it like a two-dimensional array?
Yeah, you can. You
By
can.
the same methodology?
I
Or
believe
say that
so.
The first thing is cast as a pointer, and then you do it that way.
I've never done it. Try it. Yeah, try a two-dimensional array. Go into your program, see if you can access it with one dimension. I don't think
Actually, you can. Because
you can.
That's how, yeah, that's
And
how
not
I
a C++
implement-
thing.
No, no.
Okay,
it's a
good.
C.
All right.
No, because for the CTF, I had wanted to create like the matrix, so I didn't know how to do it. So I made it.
Oh, so you did that on that level. Oh, okay,
So
all
I
right.
made 2 for loops, and then at the last loop, I just created an int m, which was the result of like every iteration the number, and it was just pretty.
You're right, because if you only give it the one dimension, then it'll be like, oh, this is your data type of that thing. I'm just going to multiply the
Yeah.
index by that data type. Yeah, so the compiler should be able to handle that.
Yeah,
This is just an abstraction for pointer arithmetic,
Yeah,
right?
Yeah.
So,
yes, basically.
You
Yes.
know, however we tell it, that's for our use.
Yeah.
not for the
And it's well known what the compiler should do in that case.
Yeah.
So yeah.
Yeah.
All right.
That's sorry. I'd like to ask like.
That's cool. All right, so consider this. This is our first example. You have a data type. You have the name of the array A, number of rows, number of columns. The data type has a size k. What is the size of a row in A? How big is this row? So this is the organization of this matrix in memory. This is the lowest address, and then it goes to an increasing number. So this is row major order. All of A0 elements are stored contiguously from 0 to the column minus 1. And then from this, the next highest address is here, row 1.
So it's just C.
It's just
Size-
C,
It's the size of C.
K times C. Good.
Oh,
Number of columns times the number of bytes for this data type, the size of the data type.
Okay.
Yep. So this whole thing is the number of columns, because there's basically C columns times the size k. Okay. What is the address of A of 25? Where's 25? Well, it's not pictured here. Somewhere in there, in this white box, is 25. What is its address?
gonna be
A plus
That was a complicated format.
C times 2, yep, plus 5, and the whole thing times k. That's it. Good, because I would rather you guys derive it than me tell it to you. Because when you derive it yourself, you'll actually remember it. And when I tell you, you won't remember anything I say. So it's good. This is what it is. It's A. And then this is the value that gets you to the right row. You take 2 rows. You know you're in the second row because this is A of 2. So you want to get rid of these 2 rows. That's what this 2 times C times K. Each row is C times K. You need to get to the row down here, A of 2 row. So that's what this is. It gets you to this element right here. And then you want the 5th one in the row. So you're taking 5, and you're taking 5 times the number of bytes in that data type. So this is the address. A gets you here, plus 2 times C to the K gets you here, plus 5K gets you where you need to go.
So wouldn't this technically be faster than using the array subscripts to get?
The array subscripts, so when you write this, the compiler is doing this. The compiler is going to be like, oh, what is that address? And hopefully the compiler can use some of the addressing logic to efficiently calculate that in one shot. That's the name of the game. And that's why you have the addressing modes, the different addressing modes. Okay, what is the address of A of ij given in terms of A, C, K, I, and J? So this would be A plus I times C times K, ik, plus J times K. Yeah. All right.
Is this what we're supposed to use on the multi?
Yes. So now you're almost able to do that. Those 2 levels, I think. Almost. I think I have to do a little bit more. Does everyone understand this formula? You need to get to the ith row. So you have to multiply. Each row is C times K. You get to the ith one by multiplying by I. And then you want to get to the jth element of this row. So then you take J times K, and that moves you to that element, broken up into two parts. Okay, so here's an example, an integer array, A of RC, and here's A of IJ. And because it's an integer, that K is 4. And so A of I times C times 4 gets you to the ith row, right? So each row is 4 times C, and you want to get to the ith row, so it's A plus I times C plus 4. And then you add 4 times J to get to the jth element. Okay, so assume we have an integer array A. Its address is in RAX. It's got an index I in RDX, an index J in RCX, and the code below moves A of IJ eventually into EAX. That's what this instruction does. Based on this assembly, derive the number of columns that are in A. Yeah, this is for you. I can give you, okay, this might be a hard get, but because you know the formula, what you want to do is you want to calculate all the values here as a function of I, J, and A. And then at the very end, figure out what is this address. And this address has to be in the form of this. And then you can derive what this number of columns is. All right, that's the trick. So here is the problem. And I'm going to give you the first part of this. RCX is J, and then you do a shift arithmetic left on it by 2 positions. This will put in RCX 4J. Right? What is the next one? What is an RDX?
So you multiply 2 RX,
2 times RDX plus RDX, which makes it 3RDX.
Which is 3 times
Or 3I.
3I. There you go. All right. I think I'll let you do the last 2 instructions because These are the money ones.
I plus 4 times j.
Isn't it 4i times j?
What's in RDX after this instruction?
4j.
3i.
3i.
So what happens when you do this?
So it'd be 12i.
Aha! 12i!
But then what about the RCX part there?
RCX is still 4j.
So, yeah, you get 4j plus 3i times 4.
12i plus 4j. All right. So, and then here's your move. And your move is nothing special. It takes the base, A, adds this, 12i plus 4j to it, and then dereferences that and puts it into EAX.
Oh,
All right.
we're supposed to-
This is your A of ij. Now, with that formula on the previous page, what are the number of columns here? You remember, I remember I-C-K.
Yeah.
Ick. I times number of columns times the size of the data type. What's the size of the data type here?
4.
Yeah, 4. I said it's an integer array, 4. So what are the number of columns? 3. Yeah.
It's a 1 by 3 matrix.
No, it's an x by 3. You don't know the number of rows. This is just telling you A of ij, and in order to calculate this, you need to skip a certain number of rows. And by skipping a certain number of rows, you have encoded the size of the row as sort of part of this, and that's why you know the number of columns. But you don't know the number of rows. It could keep on going. So yeah, here is the formula.
Oh, that's right.
And so your k is 4, and so you have 4j in there. That's fine. That gets you the, as soon as you're at A of I, the 4j gets you into the row. And then this is I times C times 4, so yeah, it's 3. This is a picture of it. And again, you don't know the number of rows, but this is basically what you have. You have a, 3, every row has 3 ints in it, and then this is the indexing code for it. Okay. So, practice problem 337, and I believe if you're able to do this, I believe that level in the homework should be doable. So here is both and it's a function that returns the sum of p of ij plus q of ji. Now, because you have two of these things, and the matrices here, p is m by n, q is n by m, now you can get both n and m with this being implemented with this assembly. Yeah.
In the homework, they're all square matrices, so we know that this number of columns is the number of rows, right? So we don't even have to do that, like this, or at least the first matrix column.
Yeah, I think one of them is like, well, this is how it is in a two-dimensional axis. Figure out how. You're right. That is the homework. Figure out what it would be for a single-dimension axis.
That's what it asks.
That's what I think. That's what that one is.
Because I don't understand that. Well, it says the output for 12 by 101 matrix, and that's, I made a matrix, but
It didn't work. All right. Well,
I don't understand what it means by output. Like, it means like, I just can't understand what that means. I
Okay.
recreated the matrix, but
try it again after this, and then see if it makes any more sense. But so do the exact for this thing to reverse engineer this thing. Figure out what's in these registers as a function of I, which is in RDI at the beginning, and J, which is in RSI. And then here, as your part of your displacement, you're symbolically using the address of P and Q. And then you're taking 8. This is your K times RDI and your K times RDX. And you have to figure out what is actually in these two registers symbolically in order to figure out the number of columns in P and the number of columns in Q, just like in the previous example. And by knowing the number of columns in P and Q, you basically know both M and N. All right. And I don't think I've animated this. I may have. But I don't want to give you the answer. So why don't I have you work on this line by line, just like you had the last time. Figure out what's in RDX. So 8 times RD. So this is 8i. And then just keep going.
Why don't they just do percentage RDI, comma 8? Why do they have the 0 and a comma 4?
That's what the disassembler emitted. I don't know why.
Some computers.
I think scaled index mode forces you to have
An offset at all times.
a base. It's basically, yeah, and you have to explicitly say that there's no base.
This function sums to vectors, correct? Like two-dimensional arrays.
Oh, I did animate this. All right, so
Oh, great.
let's walk through this. RDX has 8i. And this is how I would, like, if you're working through these problems, this is how I would annotate it. And then you're subtracting RDI from RDX. Well, RDI still has I in it, so this is basically 8i minus I. It's 7i. All right. Adding RSI into RDX. RSI is J. So now you have 7i plus J as an RDX. This is taking 4 times RSI plus RSI. RSI still has I in it, or J in it. So this is 4J plus J. This is 5J. So RAX is now 5J. Adding RAX into RDI. RDI still has I in it. You haven't changed it yet. So this is 5J plus I. Is an RDI now.
And now
Okay. So the two money instructions, we'll start with Q. This is indexing Q. So this would be this term. And you're going to take 8 times RDI. This is 8 times 5J plus 8 times I. And that is what you're going to use to move that element into RAX. So this means, what is the number of columns in Q? Based on that formula, A plus Q plus I times, well, I mean, so you don't have to ignore the lettering because the lettering got flipped. But you're taking some number of rows, which is effectively what J is, the number of rows, multiplying it by the K, which is 8, because these are long words, multiplied by the column numbers. So that is your column number, 5. So that is why the number of columns in Q is 5, which is M. So, did I get that right?
I think, no, shouldn't it be rows, columns, right? Because that's the way we had it denoted in the last one, right? So
this is the number of columns, 5, and you're multiplying, because you're going to the jth row. So I'm reusing these letters. It's terrible. It's causing a huge amount of confusion. In this case, J means the row number. And then you're multiplying it by the number of columns of Q, which is 5, and then scaling it by 8. This is going to get you to the jth row of Q. So that must mean that 5 is the number of columns in M. Yeah. And then the bottom one is 8 times RDX plus P. So that's P of IJ. So you're doing this to RDX, which is right here. So in this case, 8 times 7 times I is going to get you to the ith row. 8 is the size K, and then 7 must be the column number for P. So yeah, that's 7. Is that right? Yeah, so N is 7.
The same way the book has it.
This is exactly, it should be exactly the book, right? Ah, excellent. So yeah, this is practice problem 3. Oh, I have that misnumber.
Oh no, that's a different edition. There's
Oh,
changes.
okay. So this is practice problem 337. Yeah. Oh, you have the second edition?
No, that's like the Indian version.
The engine. All right. Okay. As long as yeah, these numbers might not be totally correct. I tried to make them accurate. Okay. This is what you've been asking about. So this is the level. This is the level in the homework. So you need this slide for it. So A of 1213, this is the declaration. you have 12 rows, 13 integers in each row. So you have 13 columns. Will the C compiler permit us to do this?
Absolutely.
A of 3, 26. Yes, the answer is yes. Even though the 26 is completely blowing up the number of columns. But what is it going to return you?
4, 13,
It's gonna keep on looking in the same contiguous memory space.
It's going to keep on looking in the same contiguous memory space. It's going to go to the third row. What is the 26th element in the third row? Well, it's going to keep on going into the fourth row. And then at the end of the fourth row, because this is divisible by 2, it's just basically 2 rows here. Yeah. It's going to give you, it's going to do the indexing, assuming the 12 by 13 array. So it's going to use the same number of columns. It's going to multiply it by the row number. It's going to do, because that stuff's baked in, right? That's baked into the compiler. You saw that in the instructions. The indexing code is baked into the instructions the compiler generates. So if you give it this, it's going to do the row calculation by taking 3, multiplying it by the number of columns that it thinks it has. So this is going to be 13 times I, which is 3 in this case. And then it's going to add the 26. It's going to go, I'm going to take 26 times 4 and get you all the way beyond that. So this is the same, because this is effectively 2 rows ahead that you're going to read. This gives you A of 5, 0. Right?
That's why you should be able to go through the entire thing at once before just by incrementing A over and over.
Yes, that is correct. Does everyone see that? Because that's the heart of the homework.
Yep. Now it's good.
Now you're good. Okay, good.
I'm so happy I constantly.
And I think the 2D array one is the previous. I think that might be the previous one. Yeah. So now both of those levels are doable.
That's pretty cool. That's pretty cool.
It's a good way to obfuscate your code.
All right. What about that? Compiler think that is everything okay here?
Sure.
14.2. And then if that's the case, where do you think that's going to go?
Won't that go off the off the allocated memory, because it still thinks there's 13 in the column?
How many integers beyond the end of this array will this go? 15. That is correct. This is adding an extra row and an extra 2 rows. Wait, no, not 15.
Then it would be
30.
28. So this is what this is doing. There's 12 rows. Wait, 0 through 11. Wait, no, way more than that. So this is numbered from 0, right? So really, this should go from A00 to A11, 12. It's just because we're the way we're numbering it. And instead of 11, you're at 14. So that's like 3 extra rows, which would be 39 times 4, because it's the integer arrays. So 39 times 4 gets you those 3 extra rows.
But you're not accessing the full.
And then plus 2 more integers. So yeah. Yeah, 2 more integers.
Doesn't it? Aren't we looking at the third row though? Beyond? Not
The third row beyond, but then 2 integers in. So
into the third row. So we're not counting the whole third row. We're just counting the first 2.
you're correct. So all right. Now I gotta. You're correct. Wait.
2 times 12. Because 12 is
13. You're right. So 2 rows, 26 integers plus 2 more, 28 integers.
It is 28.
Correct. Is that on video? Oh, too bad. You're right. That's correct. Yeah, listen to him, not me.
basic.
In basic? All right.
Now fixed in post-production, we'll put his voice. You can,
Yeah. Wait here. Hang on. Can you repeat that? All right. Yeah. You see, I'd be sitting there sleepless nights trying to figure out that. It was like, oh, I missed a row. But that's your homework. Yeah, hopefully you get your rows right.
Instead of counting sheep to go to bed, you just count arrays.
Yeah, count elements in an array. Oh yeah, so C doesn't check array bounds. And then contrast this to managed languages. If any of you have done Java or any of these other ones, that'd be like, hey, what the heck are you doing? I'm saving you from yourself. So that's what, it's like the nanny state. I'm saving you from yourself. Yeah, yeah.
But isn't the reason why they didn't fix that in the future? Like, in the future editions of C, they never like decided to implement small things like that, so they can make the language a little bit more
I think so.
user friendly.
Yeah.
Like maybe it's some sort of like other hidden condition.
Overhead. If you're always checking the array bound,
Okay.
yeah, so you could just rely on the programmer to be disciplined, which is basically what a good C programmer is, very disciplined, which is why an experienced C program is pretty valuable, because that indicates that you're actually a solid programmer in any language.
Okay.
But if you are used to programming sloppily and letting the runtime take care of everything, then you don't show discipline. Like, oh, I don't have to worry about thinking about memory because I'll just let the garbage collector take out my garbage. It's difficult to develop programming discipline. It's not impossible. I'm sure there are great Java developers out there, but it's just, that's why. All right. Wow, I'm going to have to hustle to get the, let's see here. There you go. So fixed size arrays are really easy for a compiler to optimize. So this is going to get back to when you write something in C, you might get something completely different in assembly. The compiler is trying to avoid too many calculations. And you saw with the array indexing there, that's a lot of calculations, right? Just to get one access. And so what you would like to do, especially if you're sequencing that array in order, you don't want to be calculating those addresses every single access. And so in order for you to see this translation, there's an example I want to show you, which is the dot product of two matrices, where you're taking the row, as part of this, you're taking a row of one matrix, multiplying it with the column of another matrix, and you're taking the individual elements, you're multiplying them and accumulating the sum. And so I'm going to show you this computation compiled two different ways. And so the definition, we're going to have 16 by 16 arrays. So this is a long, a two-dimensional matrix of longs, and each dimension is 16. And we're going to do a dot product. Okay, so here is some code. You have your matrix, n by n is 16. And I have matrix A, matrix B. I have the row in A that I want to multiply. I have the column in B that I want to use as K. So row in A is I, row I, and then column K in matrix B. And then what I'm going to do is I'm going to sequence through each of the elements. I'm going to use J as my integer counter. I'm going to say for every element in A, or every column element in A of I, I'm going to go from 0 to n. So this is going to iterate 16 times. And then for every element of the K column of B, I'm going to iterate. So it's going to take the 0th row, and then the first row, K, second row. So do you believe that this is going to do a dot product of I and of those two? Oh, it didn't. It didn't need to be long. This could have been an int. Oh yeah, this could have been any integer. It could have been a car. Yeah. A signed one even. And hopefully it didn't get casted. And hopefully this didn't hit 128 and get casted into 4 billion. That would have been hilarious. I should create a bug like that and then put it on your final exam. Like, what the All right, so you compiled this and without optimizations. And the compiler's just like, hey, I know how to do all this stuff. In fact, it was on the previous slide. And I'm not going to walk through this, but you can do the exact same operations that you did on the previous example and figure out that all this is doing is exactly what you did before. You know, figuring out the number of bytes, figuring out the row number, scaling it by 8, and then like accumulating that result after you dereference these two memory locations, accumulating that into RAX, which is your result. So yeah, this is a lot of shifting and adding, which is basically what you would expect to update the indices. But then you have, so if you compile it with optimizations, you'll end up with code that will look like something like this pseudocode would. So what this pseudocode is a pointer-based implementation where if you are doing a of ij, and you know this is going sequentially from 0 to n, then what do I need to do to get from a of I0 to a of I1? I need to add 8 bytes, right? Why do I have to do this again? Why do I have to recalculate that, right? I just take the previous pointer that I had, and I'll just add 8 to it, right? Because this is going in that row, it's going all the way to the right. Similarly, with the column, I'm going to go straight down that matrix. So all I have to do to get from b of 0k to b of 1k is add the number of bytes in a row. Basically, c times k. So this is what this implementation does. It's going to take these pointers, and for the matrix A, after it initializes the location at the start of the row, for every iteration of this loop, I'm just going to add one. This is pointer arithmetic, right? So this is adding 8 effectively, but you're just adding one element. And then for B, for every iteration, I'll just add n to it, which n is 16, 16 times 8, so that's basically going to go down in the column. This is easier than that. And the assembly code is similarly easy. And so you'll see this inner loop, you get an add here of 8, an add here of 128, and then you basically jump right back in here, and this is all you get, right here.
Well, that's going to be way faster.
Yeah, this one will go here, and it'll do some other, yeah. But this is slightly faster, I should say.
Oh, yeah.
And this is like our homework?
This is not,
Like the matrix multiplication we have for assignment 3?
is this your homework? No, it's not this is not assignment 3. The assignment 3 is like, why do I have to do this one at a time? Why can't I do like 4 at a time? And that's assignment 3. Yeah.
So if it's assignment, the assignment operation on, I don't have the numbers, so I can't quite say it, but the move and the iml on the 2 big lines right there, right? Those are the big, complicated, like, math things, right?
Mm-hmm.
As long as those are the same, it takes the same number of cycles to compute that thing as it does down there to compute the add.
Mm-hmm.
Sorry. Shouldn't it be the same? Because there's the same number of items inside the both loops. They're both 7 instructions. 1, 2, 3. Oh, yeah. 7. 1, 2, 3, 4, 5, 6, 7.
No, it goes down to here. Wait.
Well, you have the compare, but I guess the compare happens.
This is the reason why this is this way, is that it doesn't have to do the compare. Because as soon as you decrement the count
it's going to check
to
that
negative,
count.
yeah, it'll check that. So this is 7, this is 9.
Oh, because of the count. Sorry, I was missing that part.
Yeah, this is 9.
Reading that to be the conditional counts.
Yeah, so two assembly instructions. And we'll see, two assembly instructions, that makes a difference actually. Because it turns out you could probably do this in 1 cycle per iteration.
That's super fun.
Yeah, because you end up pipelining all of these instructions. So
Because those are all independent instructions.
they're independent, and then there's multiple integer units in the processor, so you can simultaneously execute like these adds. There's no reason these have to be sequential. We'll get to that in chapter 5 next week, but that's the idea. All right, I think that's the last thing. Oh no, the last thing is dynamically allocated arrays, which we had talked about at the beginning. So what happens if we don't know the dimensions of that array at the beginning? Well, the compiler can't give you any indexing code, which means if you want to implement multi-dimensional arrays with a length, a size that you don't know until runtime, you have to create the indexing code. You have to be the compiler, basically, is what you're going to have to do. And so, yeah, you have to You have to do that code for it to locate the data. Use malloc, but then to get the the ith row and the jth element of that row, well, malloc is giving you a flat blob of bytes, and then you have to overlay your structure, your array, your sort of the multidimensionality of your array on top of that flat byte blob of bytes. So that's why you have to do the indexing code. Or no, symbolically in your C code, you have to actually do the scaling and then multiplying and that kind of stuff.
You just have to do it in pointer arithmetic. You can't do it in like a bracket. It has to be pointer arithmetic.
Yeah, you can't use the brackets basically,
Okay.
because it doesn't know what to do with that because it doesn't have the number of columns, so it can't pre-bake that addressing code in there. So that's why.
Or you can just iterate through it like a regular array.
All right, so I've got 8 minutes. Do you guys have any questions? It's rare that I actually have time at the end of the class.
Is there any way to free a variable within scope if you have a malloc?
Oh yeah, you can write that. Yeah, you could free a variable that hasn't been allocated.
I mean, once you allocate it, if you just declare a variable.
Clear it. Doing what?
Declare it.
Okay.
Declare a variable. Let's say you declare an array within a scope. Is there any way to free that memory without having to use malloc
So malloc and free. So if you allocate memory as a local variable in a function, then as soon as you exit, it gets popped off the stack.
Right.
But
it's free at that point. But is there any way to do it before you exit the?
No. Before you exit the function, no.
Before you exit that block.
Yeah. But if you're allocating out of the heap using malloc and free, then yes, you can malloc it inside your function, use it, and then hopefully you free it before you exit that function.
So if you were working with like 3 different arrays, that you worked with one and I had to get rid of it, worked with another one and I had to get rid of it, just to save memory, because of memory constraints, then you'd want to use malloc and free within that scope, or
Yes.
jump in and out of functions to create and destroy it.
But yeah. Jumping in and out of functions will create and destroy your arrays. Yeah.
Maybe you can give me some, not only me, some hints about the struct CTF, since we have a little free time and I wanted to play with it.
Let me give you hints on levels that are doable.
Okay.
I'll take requests on levels. But not the struct one, because I have to cover structs before any of that makes sense.
The only one
Which level are people? The stack smashing ones are not throwing people for a loop. Well, what levels are? You haven't looked at them, okay.
I just finished the one from
So I think a lot of people are behind. So if you have a level from earlier that you're stuck on, rather than the ones that you're just now able to do, I don't really want to go through the array one.
Okay, the XOR ones. The only one I couldn't understand was the XOR.
The XOR.
Yeah, that one is
And
also.
the thing is, I see some XOR like in the assembly, but it's not the right XOR. And then there you have like what's that? Not masking, but where you get all the Fs, and then you have the ED at the end. Does it make sense? Like,
Mass, yeah, because I mean,
There's 3 XOR ones. There's the Chapter 2 XOR, which is pretty trivial.
No,
yeah,
that
not
was-
that one.
Chapter-
The chapter 3 one.
The chapter-
And it keeps, yeah.
There's the Chapter 3 one, XOR long, and then there's the XOR string.
well, I think they're very similar both. Like the XOR long, if you know how to solve XOR long, the string won't be so complicated.
Okay.
But yeah, because I found the XOR bit. Like I can tell what you're XORing with it, but where the data is. Like I backwards XORed every memory address.
Right.
I XORed everything. Like,
the trick that you're showing me was kind of similar, but it's that this
And actually, I'm surprised.
Let's do the string one, since
Okay.
I've already given up the string, I think, to someone. So,
trick is to look for this after
I'm going to bring up 2 windows here.
after.
Oh, I've got 4 minutes for this.
You can do it.
So then you don't have to do it. Then you just get the value. That's right.
Okay, so here's XOR string. It says code and data are often encrypted by packers using a random key. So here, find where this is happening and analyze it using. We'll use GDB. So here's my program. Where is there there's an XOR right there.
Yep, that's the one.
And so if you look at where this XOR happens, well, what is it XORing? It's XORing whatever is in EAX. Well, what was in EAX? Well, it was what was here, which is some sort of index RAX off of this base address.
But this base address doesn't like remove everything and makes it as ones, then move.
So what happens if I do this 60119F? Well, that looks like some random password, but look, this password's being XORed by 33, and then it's also being stored in place. You're basically XORing and then moving it to EDX, and then eventually the low byte of EDX, which is in DL, gets moved back into the same place. So if I run this, so if I set a breakpoint here, I'll set a breakpoint on this XOR main plus 67. I'll run, and I'm here in this XOR, and this is before I even entered the password. It's sitting here XORing. It's probably unpacking the password, and then asking me for the password, comparing it, and then doing its deed. So then if I do this again, you see it breakpoints again. So it's iterating through here, overwriting this password potentially. So if I do the x/s again.
How do you go back on commands when you have the layout open like that?
I do Control P, so it's sort of like
Thank you.
Control like Emacs. Yeah, so it's Emacs bindings, but you can do a Vim binding. I don't know how to do it, but like, yeah, Control P and Control N, and then the Control L clears it. Yeah.
GDB is a new program, so it uses read line for everything. So if you set your read line bindings to Vim inside of init folder, then your shell or bash, JSH, everything that's connected to new will convert over to Vim bindings.
Excellent. Yeah.
I did not catch.
It uses the read line package, and then that you can point to different bindings.
Okay.
But you know, this isn't the password because it's sitting there unpacked. You have to get what this is after the unpacking, right? So you know, you have to actually run this loop, and then maybe when you break out of it, here's a compare that might break out of it. Then you can set a breakpoint and see, is that your password? So that was the point of this level.
So we don't have to get the pen and pencil and convert this to
You
binary?
could if you wanted to. You could say, hey, my original string was this. I'm going to manually XOR x33 to each one of these. That's fine too. You can do that.
So on the 3.00, like the intro, there's like 3 different string compares. When you actually access the memories, is there any obfuscation past that, or is it just
No, the obfuscation is the number of times I'm calling string compare, and then if you see a breakpoint that's called multiple times, delete it because that's a bogus string compare, and I actually give you that in the level.
Oh, yeah.
All right, if you do this offline, I'll collect all your all the things.
Thank you so much for the explanation. I really appreciate it. I couldn't sleep because of that too. I lost my mind.